Hello and welcome to SRFQ for Tutorial Reinforced Concrete Design. And for today, we will be reviewing the flexural analysis of beams, wherein this subject actually supposedly is more focused on the design of the reinforced concrete components, but for the sake of the others who are still having difficulty understanding the analysis part of this material, we will be covering a review of some of the uh, reinforced components that needs to be designed. Okay, so for today we will start with the review of lectural analysis of beam. And for our session today, here's our outline and outcomes. So we will start with discussing the stages of concrete before it reaches failure, or the reinforced concrete before it fails. Then we will also discuss what is the formula used for the modulus of rupture and also what is cracking moment. Okay, so for the outcomes of this session, we have the following. Our objective is to outline the different stages that reinforced concrete undergoes prior to failure. But for this session, we will just cover the first one. Okay. And then to demonstrate to you the governing formulas in calculating the modulus of rupture and cracking moment, and then apply it to two examples on how these formulas are used. Okay, so to start off, let us um, define or state the different stages, distinct stages that a reinforced concrete undergoes before it fails. Okay, so generally we have three stages. We have the first one, uncracked concrete stage, stage two, concrete crack elastic stresses stage, and then lastly is the ultimate strength stage. Okay, so basically it means that when we cast our reinforced concrete, it does not mean that the reinforcing bars are actually working already. Okay, so there is a time that when our member is not yet subjected to its loading, um, the concrete itself is behaving as a whole. So the compression and the tension side are both working. Unlike when you reach a certain point, the tension part of our concrete will be neglected already because we assume that it's already cracked, and when it's cracked, it cannot carry any more forces or cannot um, provide resistance to our loading. Okay, so for today again, we will just focus on the first one, which is uncracked concrete stage. So what do we mean by this stage? But before that, we will introduce first the formulas that we will be using when we analyze uncracked concrete stage. Let's start off with the modulus of rupture. Okay, modulus of rupture, according to our code NSCP 2015, section 4192.3.1, page 4-129. The modulus of rupture, or designated as F sub r, for concrete shall be calculated as follows. Okay, so we have Fr is equals to 0.62 lambda square root of F prime C, wherein C lambda is taken as 1.0 for normal weight concrete. So if it will not be a normal weight concrete, there is another page or section in the code wherein you can choose the value of lambda depending on the condition of your concrete. But for our case today, we will just focus on lambda is equals to 1.0. And then we have the F prime C, or the compressive strength of our concrete material. Okay, so when calculating for the FR, we see here that we just substitute the values. Okay, so what does it mean? Once we know the value of FR, we can actually compare the values of our bending stresses of the top and bottom fiber. And then from there, we can say whether our concrete experienced cracking already. Okay. But to continue with the uncracked concrete state, we should also know what is cracking moment. And this is also given by NSCP 2015, section 424.2.3.5, page 4-158, wherein the cracking moment MCR of concrete shall be calculated as follows. We have MCR is equals to the modulus of rupture times the gross moment of inertia over the distance of the extreme tension fiber from the neutral axis. Okay, so from your prior knowledge with reinforced concrete, as you can see here, the distance na we considering is the one from the tension fiber, because as we have, or I hope you already know, when our concrete or our beam, for example, is subjected to bending, let's say a positive bending, the top portion or the top part is in compression, and then our lower portion is in tension. So how does it work? So let's say this is our beam in longitudinal view, and we have our supports. Okay, once we apply loading, okay, let's say a uniformly distributed load, what is our elastic curve, or what does our elastic curve look like? So it means that exaggeratedly, it will look like this. Okay, wherein our beam tends to compress on the upper side, that's why it's in compression, and then on our lower part, it tends to elongate or in tension. Okay, so our neutral axis is the location wherein this changes does not exist. That is why it is located here. And in reinforced concrete, we assume that this portion for the reinforcing bars, we are um, reinforcing our concrete with rebars at this location. For the reinforcing bars to work, or before it works, the tension side should crack, or the tension crack. The tension side should be already in crack condition. That is why this portion is actually neglected, and then we are just trying to look for the value of the moment that will produce cracking on that side. That is why we get the value of y from the modulus, from the cracking moment formula, from the extreme fiber of the tension side. Okay, that is why YT. Then we have gross moment of inertia. If ever our section is irregular shape or not rectangular, we will just use transfer formula to get the overall inertia of the components with respect to a reference axis. Okay, and then as stated here, as the load is increased after the modulus of rupture of concrete is exceeded, so um, until FR is reached, or the moment cracking is not reached, or until it's reached, the cracking will start to develop. Like I've already mentioned here, when cracking already developed, the tension side of our concrete is considered uh, negligible already. So it's not working. That is why the one um, counteracting the forces um, generated by this loading is the rebars, or the reinforcing steel bars that we try to provide on reinforced concrete. Okay, so the moment at which this cracking begins to form is referred to as the cracking moment. Okay, so we are trying to identify what is the value that will tend to crack uh, our beam on the tension side. Okay, so that is what cracking moment means. Okay, so these two formulas, the modulus of rupture and the moment cracking formulas, are important in discussing the first stage, because we need to verify if our concrete is really is really uncracked or not cracking yet. Okay, so to discuss the first stage, we have here the uncracked concrete stage. So when tensile stresses are less than the modulus of rupture, Okay, it means when we calculate the stresses for the um, compression fiber and then the tension fiber, the tensile forces is less than the modulus of rupture. It means that the entire cross section of our beam, or the whole rectangular section, resist bending. So the rebars on the tension side are not yet working. So we can actually just utilize the concrete itself um, to resist the loading that we have. Okay. So to demonstrate this further, we will solve two example problems to um, more appreciate what is happening on the uncracked concrete stage of concrete. Okay, so we have the first one. Okay, so assuming that the concrete is uncracked, okay, so we will, although it's already stated that it's uncracked, we will still verify it later. Compute for the bending stresses in the extreme fibers of the beam. For a bending moment of 30 kilonewton meter, the normal weight of concrete has a compressive strength of 27.6 megapascal. Compute for the cracking moment of the section. Okay, so we have here the dimensions of the section. We have a 300 by 450 reinforced concrete beam with 328 millimeters diameter bar. Okay, we have here the location of the centroid of our rebars from the extreme fiber, which is 75 mm. So concrete cover is 75 mm. And then we are given, let me write this, we are given with a loading, a bending moment of 30 kilonewton meter, and also the compressive strength of concrete is 27.6 megapascal. Okay, so the first question is compute for the bending stress. Okay, bending stress of the extreme fibers of the beam. So when talking about bending stress, we have a formula for bending stress, which is mc over I, wherein c represent the distance from the neutral axis from the extreme fiber, and then I is just inertia, and then m is for moment. Okay, so if it's uncracked, okay, it means, based from our previous definition, that the concrete is working as a whole. Okay, so if our shape is a rectangular section, excuse me, it means that our neutral axis is acting where? It is acting at the mid height of our beam. So we can say that this location is actually 225, or the half of 450, and also this location is also 225. Okay, that is our neutral axis. So if the value of the distance from the extreme fibers are the same, we will have the same value of bending stress for the top fiber and the bottom fiber. So we can say that our F top and F bottom will be equals. Okay, so let's calculate that. So let's consider, let's say, the top fiber. So we have the moment, then the distance, and then the inertia. So uh, for rectangular section, the uh, moment of inertia is base times height cube over 12. Okay, so we substitute the values. We change the value of kilonewton meter to Newton mm to uniform the unit. Okay, and then multiplied by the distance from the extreme fiber, so from the neutral axis going to the extreme fiber, that is 225. Okay, so we have 225 mm all over. The inertia is 300 mm multiplied by 450 mm cube over 12. Okay, so to calculate this, you just need to input it in your calculator. So let me pull out our calcu. Okay, so let us try to encode this. We have 30 times 10 to the 6 times 225 all over our value of 300 mm times our 450 height cube all over 12. Okay, so we have a value of 2.962. 2.962 megapascal. So that is our bending stresses for the top and bottom fiber. Okay, we already have the value. So we need to verify if it's really uncracked or the concrete is really uncracked. So we need to get the value of our modulus of rupture to compare it with the value of the bending stresses that we have calculated. So let us have here the formula for our modulus of rupture. Okay, is equals 2.62 lambda of square root of f prime c. We have 0.62, we have 1.0 for lambda. Then the value of the compressive strength is 27.6. So MPa. So try to calculate this. So we have 0.62 times 1 times square root of 27.6. Okay. So we have a value of 3.257 megapascal. Okay. So since our bending stresses for our bending stress at top and bottom is less than with our modulus of rupture, therefore no cracking occurs. Okay. Next, after having verifying if it's our concrete is indeed uncracked, it is tasked or asked to compute for the cracking moment of the section. And since we already have the value of FR or the modulus of rupture, let's just plugging in formulas. We have MCR is equals to FR I over Y bottom or Y at the tension side. Okay, and we have 3.257 megapascal. So that is Newton per mm squared, equivalent unit. Then for inertia, we have again 300 mm times 450 mm cube. We have over 12 all over the distance from the neutral axis. Okay, again neutral axis to tension fiber, that is also 225. Okay, so substitute it here. So we have 225 mm. So what will be the unit? So here so this is moment. Okay, moment, the value is moment. So we have the answer here will be mm to the fourth. We will cancel out 2 here. This will be 2, and then we will cancel 1. The resulting moment value is in Newton mm, or if we want to reflect it in kilonewton meter, we just divide it by 1 million. Okay, so let's have that. So based from this value, okay, let's pull out our calcul. Okay, so 3.257 times 300, times 450 cube over 12 all over 225. Okay, so this is the value if it's in Newton mm. So I will we'll write that. So 1.669. Okay, so let me check if it's our calculation is correct. 450 cube over 12. Okay, what happened? Let us verify this. Cube over 12, 257. 3.257 times 300, 450 cube over 12, then divided by 12 times 225. So y. Okay, and all over. Okay, yeah. 225. Okay, so this is more, I think, the correct value. So we have this is 32,977,000. Okay, so if you want to make it kilonewton meter, we just need to divide that by 1 million or 10 to the 6. Okay, so let me rewrite this. 77125. Then to make it kilonewton meter, just divide it by 1 million. Then we have 32.977 kilonewton meter as our cracking moment. Okay. So this is our answer for this problem. So looking at our answer, we can see that the value of the cracking moment is 32.977. It is greater than on our applied moment, which is 30. It means that our loading, or when 30 kilonewton is loaded in our beam, the tension side does not crack yet because the capacity of the concrete itself is still sufficient to support the 30 kilonewton meter force. Okay, that is why this particular concrete is experiencing the first stage of the process only. Okay, all right. So let's have another one. Here we have a T-beam. So if the T-beam shown is uncracked, okay, we will still verify that later. Calculate the stress in the concrete at the top and bottom fiber under a positive bending moment of 100 kilonewton meter. Then if F prime C is 20.7 megapascal and normal weight concrete is used, what is the maximum uniformly distributed load the beam can carry if it's used as a simple beam with 7.5 meter span without exceeding the modulus of rupture of concrete? Okay, so a quite lengthy problem, but let us solve it one by one first. So we have here a T-beam that is said to be uncracked. Okay, so although stated, we will verify later. Okay, the first question is to calculate the stresses on the top and bottom extreme fibers. So with regards with our shape right now, the value of the top and bottom fiber, the distance of the neutral axis, will now be different from the bottom and the top fiber of our beam. Okay, so let us assume that is the location of our neutral axis. So just assume first the location. And then to get the value of its distance, we need to take we need to subdivide the shape into regular shapes and then take the moment area of each shape and then get the distance of the whole component based from a reference axis. Okay, so let us assume that the bottom fiber or this location is our reference axis. Okay, and then we divide the section into two rectangles. Let us call this shape 1 and then shape 2. Then the centroid of these shapes are have a distance of, let's call this as y1 and y2. Okay, so to get the value of the neutral axis from the reference axis, so this is that location. Let us call this y bar, or um, the distance of the neutral axis from the reference axis. Okay, so to get the value of y bar, we can get the components, what we call that, components method, okay, of solving for the centroid, or um, the composite method area. Okay, so what it says is the total area times the or the area of the component multiplied by the centroid of the component, or the shape, is equals to the summation of the area of the divided, or the component. So the composite part. Okay. So to get to y bar, we just need to um, calculate this value. Okay. So for our first area, okay, so shape 1. So this is our shape 1. That is a rectangle. So the area is 15 mm times 125 mm, for a total of 187,500 mm squared. Okay. Its distance is this part. Okay. So we have the total height. So 675 and 125. So we can measure that out. That is 800 mm. So to get this height, we just need 800 minus this small portion, which is what, 1/2 of 125. So let us get that. So we have 800 minus 1/2 of 125. This is in mm. So we have y1 is equals to 800, 125. So we have 737.5 mm. Okay. Next, for our second shape, we have the second shape, which is a rectangle also, with dimension 300 by 675. So the area will be 300 mm times 675 mm. So just need to calculate its area. So let's have here. So that is just 300 times 675. So 202,500. Okay. Then for y2, looking at the figure, this is the centroid. So that is just half of the height. So we need 675 mm divided by 2. So that is 337.5 mm. Okay. So once we have that, we can now substitute it in our equation here at the top. Okay. So summation of the area times the centroid, we have 187,500 mm squared times the 737.5 mm, plus we have 202,500 mm times 337.5 mm. Okay, this is squared all over our total area is 187,500 mm squared plus 202,500 mm squared. Okay, so the unit will be mm cubed on the top, mm squared at the bottom. Canceling it out, we will have only. Okay, so what will be the value of this number? Okay, let us try to solve it here. So we have 187,500. We have 737.5 plus 202,500, then 37.5. Okay, all over our total area, which is 187,500 plus 202,500, and equals. So we have a value of 529.8. 529.8. Okay, so that is the distance from the bottom. 808. Okay, so that is this distance. Okay, and when we have that, that is our distance from the neutral axis going to the extreme tension fiber. So we can actually call this one as our y bot. Okay, and for the y top, you just need to minus from the total height, which is 800, the value of bar y. So that will be 800 minus 508.808. So showing it here. Okay, so let me store this value in one of our letters. So 800 minus the stored value. Okay, so we have 270.192. Okay, so that is our y top and y bottom, or the distances of our extreme fibers. So why do we need to get that? Because we are tasked to get for the value of our stresses at the top and bottom extreme fibers. And we will use that on the formula for the bending stress. Okay, so going back here, so we can now calculate the value of our bending stresses. For the top, we have M y top over I, but we don't have inertia yet. Okay, so we can also get that first. Okay, so okay, so let me erase this one first. Then let us get the formula for inertia. But this is a composite shape, so we need to use transfer formula for this. So we have the inertia of the whole cross section is equals to the summation of the inertia, gross inertia of individual plus the area times the distance from the neutral axis to the centroids of each section squared as our inertia. So how do we determine that? So based from our figure, this will be our D1 and this will be our D2. Okay, so according to this figure, we can calculate D1 as how? We have the total height of this, which is y top, which is 270, minus 125, half of 125, which is this one. Okay, then for D2, okay, we already have this distance. We just need to diminish the half of 675 to get D2. Okay, so let us perform that. So inertia of the first one. So we have 1,500 times 125 cube over 12 plus 1,500, the area, 125, times the distance, as we mentioned earlier. So I'm neglecting sign first, no? So we have 270.192, that is yung y top, minus the half of 125, or the flange, the height of the flange, over 2 squared. Okay? This is for the first shape, plus the second shape, we have 300 by 675 cube over 12 plus 300 times 675 times the height will be our y bottom, which is 508.808, minus 1/2 of our height, which is 675. This is our second inertia. So to get the inertia, just need to input this. Okay, so we calculate first the first one, so that we will not have error. So we have 15 times 125 cube over 12, okay, plus 1,500 times 125 times 270.192 minus 125 over 2, then squared. Okay, so this is the first part. Let us store it to another letter or constant. Let us say b. And then the second one, we have 300 times 675 cube over 12 plus 300 times 675 times the 508.808 minus half of 675 over 2, then squared. Okay, so we have the second value. And then to get the sum, we just need to recall the functions of b plus c. So we have this value, 2.196. 2, okay, 2.196, okay, times 10 to the 10. mm to the 4th. Okay, so that is our inertia. Okay, so now that we have our inertia, I think we can now calculate the value of our stresses. Okay, so we have now inertia and the distances from the neutral axis of the extreme fibers. So we now can get the value of F top and F bottom. So we have M Y top over I XX. Okay, so we have the value of our moment is 100 kilonewton meter. Okay, so let's do that. So 100 times 10 to the 6 Newton mm. Okay, I'm converting already. And we have, for top, we have 270.192. All over 2.196 times 10 to the 10 mm to the 4th. Okay, so what will be our unit? Mm will be cancelled out, so there will be a 2 that will remain on the bottom. That is Newton per mm squared, or just megapascal. Okay, so before we calculate, let us also rewrite the formula for the extreme bottom fiber. We have 100 times 10 to the 6 Newton mm multiplied by our value of bottom, which is the centroid, 508.808. Sorry, 508.808 mm over 2.196 times 10 to the 10 mm to the 4th. Okay, cancelled out. 2 remains, so we also have megapascal. Okay, let us calculate this one. So allow me to, okay. Okay, so let us try here. So we have 100 times 10 to the 6 multiplied by 270.192 all over 2.196 times 10 to the 10. Okay, so for the top fiber, we have 1.23 megapascal. Okay, then for the bottom fiber, we just need to change the value of y. So we have 508.808. We have 2.32 megapascal. Okay, so based on our calculation, this is the value of our extreme fibers. Now, to verify our assumption that it is uncracked, we need to calculate the value of our modulus of rupture. So let us indicate it here at the bottom. We have Fr is equals to 0.62 lambda F prime C, that is 0.62. Okay, 1.0. Then F prime C again is 20.7 megapascal. So Fr will be equals to 0.62 times 1 square root of 20.7. We have 2.82. Okay, that's our value for Fr. And as you can see, both values are less than our Fr, which means that there is no cracking. Okay, so we verified that already. Now we go to with the second question. Okay, the second question is, what is the maximum uniformly distributed load if the beam carries a simple beam with 7.5 without exceeding the modulus of rupture? So we need the value of the modulus of rupture. So let me copy this one. Okay. Then we have a simple beam. So going to another slide. So we have a value for modulus of rupture. Okay. So we have a beam, a simple beam. Okay. And it's loaded with uniformly distributed load. Now we don't know the value, that is the unknown, so that is W. Let's say W. Then we have our length. For a beam loaded with uniformly distributed load, what is the maximum moment? Because we need the value for the moment to get the value of the uniformly distributed load. So based from your structural theory, this one will be equals to W over 2, or the equivalent concentrated load of the uniformly distributed load is W times L, which is located at the center. And then these two support will support this load. evenly. That is why WL over 2. Okay. Then when we construct its shear and moment diagram, we have here, this will be our WL over 2. Then since this is uh, a first degree curve for a rectangle, the next shape is a triangular shape. Okay. Then based from here, that is negative WL over 2 because it's just below WL, and then the concentrated force from the reaction will tend to return it back to the 0 side. So this is our shear diagram. For our moment diagram, the maximum moment is located where the zero shear happens. So our moment, since this is a linear curve, so or a triangle, the next is a parabolic curve. So we can assume that that is that point. Okay, and this point is the area. This area, that is, this is L over 2. So that's the area is 1/2 WL over 2 times L over 2. So we have WL squared over 8. So that is our maximum moment. Okay, that is why it's always given like that. Max moment is equals to WL squared over 8. We have the value, the formula for cracking moment is equals to FR I over YT. We already have this value on the previous slide and also this value. We also have this value. So we can equate these two equations together to get the maximum uniformly distributed load that will give us the value before the concrete cracks. Okay, so equating these two, we have WL squared over 8 is equals to FR I over YT. So retaining the W part on the left side, we have 8 FR IG, okay, over YT, or Y tension, or Y bottom, okay, L squared. Okay, so let us substitute the values. We have 8. Then for FR, we calculated 2.82. That is Newton per mm squared. We have the value for I. Let's look at 2.196. Okay, 2.196 times 10 to the 10 mm to the 4th. For Y bottom, we have 508.808 mm. And for the length, it's given that it has a span of 7.5 meters. So we can put 7.5 times 10 to the 3 to make it mm squared. Okay, so what will be the unit? This will be cancelled out. Mm squared will remain. Then at the bottom, it will be mm cube. So cancel out this 2, then 1 will remain. So we will have a value of Newton per mm, or the same as kilonewton per meter as our uniformly distributed load. Okay, so let us calculate this. So 8 times 2.82, okay, times 2.196 times 10 to the 10 all over 508.808 multiplied by 7.5 times 3 squared. Okay, so we have 17.31 Newton per mm, or that is also equivalent to 17.31 kilonewton meters when you convert Newton to kilonewton and mm to meters. Okay, so this will be our answer for this problem. Okay, so there you have it. When you check whether your concrete is uncracked, you just need to calculate for the bending stresses of your extreme fibers and then try to get the value of the modulus of fracture or the cracking moment and then compare it with your values. Okay, so for this example, we didn't calculate the value of MCR because we already know that the value of the bending stresses is greater than the value of our actual stresses for the top and bottom fiber. But for the sake of calculating for the MCR, let's try. We have here, okay, MCR is equals to FR Y bottom over IG or IXX. We have 2.82 Newton per mm squared. We have Y bottom is 508.808 mm. And we have for the inertia, let us look at here, 2.196 times 10 to the 10 mm to the fourth. So you can see what will be our unit. So this will be okay, so wrong formula. Okay, so I get confused here. FR I over Y bot. Okay, so this will be 1.2 2.196 rather 2.196 times 10 to the 10 mm to the fourth all over 508.808 mm. Okay, so mm squared, so this will be mm squared, then this will cancel out the one, then we will left out with Newton mm, then just divide it by 1 million to make it kilonewton meter. Okay, so let us do that. So we have 2.82 times 2.196 times 10 to the 10 all over 508.808. We have this value, then let us divide that by 1 million. So we have 121.71 kilonewton meter. So this is the capacity of the concrete itself. That is the meaning of that value. Wherein it can carry until 121.71 kilonewton meter of force without even using our reinforcement. And based from our loading, we only have 100 kilonewton meters. So indeed, our concrete itself can support the given loading even without reaching the cracking stage. Okay, so this is the discussion and formula or sample problem for the uncracked concrete stage. Next module, we will start with the other two stages and we'll try to verify what happens when the concrete has cracked. Okay, so for question, you can leave your comments below or you can contact me directly face to face. Okay, so thank you guys for listening and good day.